this part, but like low, high, low, something like this. This PNA pattern. But in January, but December, the teleconnection pattern is somewhat different from January. It's particularly over the East Asia or Western Pacific, this teleconnection pattern is quite different. So you can see there is a considerable magnitude of the anticyclone here. Okay? So I call it a crucial anticyclone because this location is a crucial expansion region. So this crucial anticyclone is quite important for East Asian climate. Because there is an anticyclone here, then there is a northerly wind. Northerly wind provides warm and moist air to the East Asia. Then we can expect some warm winter and some more precipitation. So that's why there are positive correlation over the in early winter over Korean Peninsula. So this anticyclone is quite important. Also, there's some in the northern part there is a cyclone here, so kind of some dipole pattern. However, in January, this crucial anticyclone is abruptly gone. So nothing here, even it's negative. Okay. So I used some NDJ linear 3-point SST. So as index is exactly the same, but it's a teleconnection pattern. It's quite different. Okay. So I calculate the pattern correlation. This one is 0.46. If we focus on this East Asian region, then pattern correlation is even lower. So anyway, this crucial anticyclone is quite important to explain the impact of ENSO on Korean Peninsula or East Asia. Then question is what makes this difference? So I introduced some SST to precipitation, precipitation to teleconnection, right? So I checked step by step. So this is the teleconnection pattern. It's a pattern correlation is 0.46. Then I checked SST. This is a December SST and January SST. It looks quite similar. So pattern correlation is 0.99. That means almost same. Same SS forcing, but teleconnection is quite different. Okay. Then I check the precipitation like this. Can you find some significant difference? Looks similar, but okay. Because he's our course over one paper, so he has to know. He has to know. Yeah. But anyway, it looks similar. Okay, but later I will emphasize some difference. But it looks similar. So pattern correlation is 0.86. Okay, so almost same. So in linear sense, we cannot explain this so much difference. So we can maybe we may blame there is due to some noise. So it's not signal. Okay. So this pattern difference is quite important to explain this one. So you can see in December there's a very high correlation here, but in January this crucial anticyclone abruptly disappear. So its correlation is very low. By the way, if you have any question, you can ask me immediately. So just for Korean Peninsula, so I check some correlation like some global map. So you can see in November, December, there is a significant correlation over East Asia in November and December, but January, because crucial anticyclone disappear, so in January there's even negative correlation. So positive correlation is on here. So I will emphasize, but this positive correlation is related to some Philippine Sea anticyclone. It's a Binois, Professor Binois emphasized. Okay, then let me explain. What make teleconnection difference. So I I tried to zoom in the December and January precipitation, so you can see. So there are main characteristics are like two kind of precipitation anomaly. See, there is a positive Central Pacific precipitation here. So usually to address the El Nino impact, we emphasize this Central Pacific precipitation. So this diabatic heating makes some extratropical teleconnection via some loss wave propagation. So there is so course of the PNA, it's Pacific North America pattern. But there is a comparable negative precipitation. Also well known. This is also well known. This is a negative precipitation over the Western Pacific here. Particularly the Western North Pacific is quite important. But it's a general pattern seems very similar. But if you look at very carefully, then we can find some difference. Firstly, this precipitation is slightly increased from January to December. Also, if you check the Western North Pacific region here, then this precipitation is slightly decreased. Okay, do you agree? Anyway, so there is very slight difference. Okay, but then I will argue this slight difference can make a huge difference in an El Nino teleconnection. Okay, so but it's before answer my question. So new question is what are our relative roles like to precipitation in ENSO teleconnection? We know where this role of this precipitation, but so far we doesn't pay attention much like this Western North Pacific negative anomaly. So I want to separate the effect of the two precipitation patterns. So to separate statistically, I applied this multiple linear regression. So our teleconnection is like some geopotential height in middle latitude can be divided like two terms, like this Central Pacific precipitation, then it's a Western North Pacific precipitation. Then alpha is a multiple regression coefficient. Then this is a precipitation. So we can reconstruct. Anyway, then we can calculate alpha and beta. So alpha can be interpreted as the impact of Central Pacific precipitation. Then this beta can be interpreted as the impact of the Western North Pacific precipitation. So this is alpha and beta. So you can see Central Pacific precipitation is related to this overall cyclonic flow of the North Pacific. Okay, but Western North Pacific, by the way, this is actually this is a minus. So I multiply minus. So this is for the negative precipitation. The response for the negative precipitation. Then it's beta is a pattern similar. But it's minus, so there is a anticyclone flow. But as you may expect, the precipitation pattern is a shift to the Western Pacific because this is located Central Pacific, this is Western Pacific. So this teleconnection pattern related to teleconnection pattern is also shifted to the west. Okay, but important thing is the magnitude. The magnitude is it's quite similar. It's very difficult to say which one is dominant. Okay? But over the Eastern Pacific, it seems this impact is larger than Central Pacific, that of Central Pacific precipitation. Okay? So okay, this is like observational composite of El Nino composite. So November to February. I emphasize this December to January. So there is a strong crucial anticyclone here. But it's a little bit weak, but this crucial anticyclone is so abruptly changed like this. Then we have some alpha and beta. Then there is a seasonal evolution. It's an evolution of a precipitation anomaly, Central Pacific and Western Pacific anomaly. Then we can make some reconstruction based on this multiple regression. So if this figure is similar to this figure, then we can say this multiple regression coefficient or precipitation anomaly can explain this seasonal evolution or seasonal locking to Elliott-Taylor connection. So I did a reconstruction, so like this. Of course, this reconstruction is not perfect, but this reconstruction captures major features. November to December, there's a crucial anticyclone here. Also, there's dipole pattern, like observation. But in January, this anticyclone is considerably weakened here, like here. Okay? That means this multiple regression can explain this change, seasonal dependency. So there will be two parameters. Alpha, maybe alpha will be quite sensitive to the season, or beta, or this precipitation. Precipitation change is quite big from December to January. Okay? This is the El Niño case. In La Niña case, even better. In La Niña, it's composite November, December, January, February. So there is a crucial cyclone now, cyclone here. Then during La Niña period, there is some cold and the dry condition of Korean Peninsula. Then in January, this cyclone is abruptly gone, disappear, like this. If you apply multiple regression, I mean, it's reconstruction based on multiple regression, then this reconstruction nicely capture this cyclone here, then it's abrupt change of the cyclone. Okay? So what makes this seasonal difference? So as I mentioned, there will be two factors. Maybe alpha is seasonally dependent, or it's a precipitation anomaly. So this is December and January. So I used some multiple regression with seasonality. But in this figure, I used the same alpha in December and January. So in that case, we can exclude the effect of the varying this alpha and beta, seasonality of alpha and beta. Then, but little bit weakened, but even we use some same alpha and beta with the season. Their major feature is December to January. Capture well. That means this alpha and beta is not a big contribution. This precipitation change from December to January is a big impact. But as I mentioned before, this precipitation change is looks like it's invisible, right? It's very small. Okay? Then how this small change can make some big, huge difference in teleconnection? So I want to discuss this point. So why a teleconnection dramatically changed the slight change of the tropical precipitation? So as a given month, we can say it's a teleconnection is determined by this precipitation. Central precipitation and western precipitation. Then the stream function or geopotential height can be written down like this. This is a linear operator. This precipitation and western precipitation. If you apply this equation to multiple regression, this L1 is alpha, L2 is beta, and this precipitation anomaly. Okay. But we found this operator and this operator, the magnitude of two operators are comparable. Very similar magnitude, but sign is exactly opposite. Okay? So this is almost cancel out. Then also sign is also opposite. So this is a bigger one. Also, this is a bigger one, but cancel out. So cancel out, make this small one, right? So order. If you compare order, this is a teleconnection. Then it's like impact of the central Pacific or impact of Western Pacific precipitation. It's like it's a lower order. Okay, it looks like some geostrophic and ageostrophic. You know, it's in geostrophic balance. The Coriolis force and pressure gradient force is balanced. I mean, they are dominant term, but their magnitude is quite big, but it's like cancelled out. So ageostrophic component is one order lower than geostrophic component. Okay, it's the same thing. Because this operator is larger, but it's this size is like lower. Then we may consider slight different ones. Then change of teleconnection, because we assume this L1 and L2 operator is same with Sweden, because I showed already the alpha and beta is doesn't matter. Yeah, seasonality is doesn't matter, right? Anyway, then it's like write down like this. Then delta psi, this is a seasonal change of the teleconnection, can be write down like this, But you have to remember this delta CP and delta WMP is the same sign, because I mentioned the from December to January, the central precipitation is strengthened, right? That means positive to strong positive, then it's positive, right? Then Western North Pacific is a strong negative to little bit moderate negative. Then it's also delta precipitation is positive. Then positive. In this equation, these two terms are opposite. But in this equation, this delta precipitation and delta WMP is the same sign. So now, this magnitude of delta psi and psi is the same order. Usually, delta is like a low order, but it's the same order. That means that this the teleconnection can be significantly considerably changed. Even sign can be changed because order is same, like plus O to minus O, something like this. Okay. So from this simple discussion, we may expect this teleconnection can be dramatically changed with a seasonal evolution. Then how much different in tropical precipitation? So I calculate then central Pacific precipitation and Western North Pacific precipitation, a linear composite and non-linear composite. So during a linear case, like a 16% increase, then 22% decrease. Then non-linear case, 6% and 24%. So about 10 to 20% increase or decrease. But this 10 to 20% decrease, that means it's one order lower than this precipitation, make some big difference, like this precipitation. Okay. This figure is show the explained variance. So usually, if we only consider central Pacific precipitation, then we can explain this some geopotential height is interannual anomaly of geopotential height, something like this. Correlation is like 0.6 here. This PNA pattern is dominant, but very weak predictability. This is a kind of predictability. This is very weak predictability. But if we consider two effects, it's a Western North Pacific precipitation and Central Pacific precipitation, then it's like explained variance is considerably increased. So difference like this. So the one take-home message is this Western North Pacific precipitation is quite important for explaining the East Asia climate. So far, I showed some statistical analysis. So to support this observational argument, I carried out some numerical model experiment. I used the LBM. LBM is a linear baroclinic model developed by Professor Masahiro. anyway, this is observation. I showed this is December and January. Then I use some December forcing and December basic state. Then LBM nicely, not much nicely, but it's LBM captures the main features like a Croatian anticyclone here. There's kind of some dipole pattern. Then it's like a PNA pattern. Okay. Then if we use some January basic state and January tropical forcing, then it's explained. This Croatian anticyclone is suddenly disappear. So it's quite similar to observation. That means this model. This model has only two information in terms of seasonal evolution. First one is a basic state change. Second one is a tropical forcing change. I will show exactly, but it's even we use the same basic state. If we only consider the forcing difference, also it's a model produces such kind of some difference. That means the tropical forcing is important to explain this seasonal evolution. So how to explain this one? Then LBM is a linear model, so we can separate the tropical forcing. So this Western Pacific and the Central Pacific. So you see this weakened Western Pacific and strengthened the Central Pacific. So you see this is a response to each forcing. So in December, like this, the Western Pacific forcing can produce a Croatian anticyclone here. But Eastern Pacific, Central Pacific forcing has an opposite precipitation. But if you compare the magnitude, this one is a little bit stronger. That's why this forcing produces this Croatian anticyclone. However, in January, general pattern is quite similar between December and January. But for the Western Pacific forcing, the magnitude is a little bit weakened. But for Central Pacific forcing, this magnitude is a little bit strengthened. So if you compare some two effects, then this one is dominant in January. That's why there's no Croatian anticyclone here. So from the LBM experiment, we can make a conclusion. It's the same conclusion with the observational argument. Okay. Next, so we also analyze semi-final models. We use historical one is like 40 models because there are two regions to analyze semi-final models. First one, we are using some climate model for seasonal prediction, but we found some important fact, some Western North Pacific, the role of Western North Pacific precipitation, or some opposite effect of the Central Pacific precipitation, Western Pacific precipitation. So we need to understand what is a systematic bias in simulating El Niño teleconnection. So that's why I analyze semi-final models. The other reason is because we use only 30-year observational data, but 30 years is maybe like a 7 to 8 El Niño case. It's a case is small, but in semi-final model it's like 100 year, then 40 climate models like some looks like 4,000 year data. So there's a large data. So this kind of some big data, we can support some our observational argument. So basically I did the same analysis to the semi-final models. This is a multi-model ensemble. So this is observation and the semi-final. So in November, December, you see there's a significant difference in observation. But in model, the general pattern are similar, but I want to tell you that there are three systematic problems. First one, general magnitude of teleconnection is weak. Okay. Second one, particularly over the East Asia, this Croatian anticyclone, the magnitude of Croatian anticyclone is too weak. in semi-5 models. Third one, I emphasize this abrupt change of Croce anticyclone. But in semi-5 model, there's Croce anticyclone weak, but almost same, but even stronger in January. So model failed to simulate this abrupt change of Croce anticyclone. So I mentioned the 3 point. Then how to explain this bias, this problem? So I compare the tropical forcing because I emphasize the tropical forcing is important. So this is November in December, January. In tropical precipitation, also we can notice 3 problems. First one, in general, it's a magnitude of precipitation anomaly. It's weak compared to observation. Okay, Central Pacific Western must be. Second point, compared to Central Pacific anomaly, the Western North Pacific precipitation is too weak compared to observation. Okay. Third one, in observation, this precipitation is a little bit weakened. But in the semi-5 models, this precipitation is even stronger. So I mentioned the 3 points in the teleconnection pattern. Also, I emphasize 3 points in tropical forcing. They can be matched. So this is each model, individual model. So in general, this is observation. This is a multi-model ensemble. In general, it's most of semi-5 model underestimate the Western North Pacific precipitation anomaly. Then also underestimate the Central Pacific anomaly. But this underestimation is more severe. So this is a summary. So overall weak teleconnection over North Pacific, and particularly weak Croce anticyclone, no rapid decline of Croce anticyclone in January. Then that problem can be explained as weak precipitation, weak negative precipitation, and strengthened West North precipitation in January. Okay? So this systematic error support our observational argument. Okay? This I checked only this multi-model ensemble, but we have 40 models, so we separate 2 groups. So it's a strong. We selected 10 models, which simulate strong negative precipitation. Then also selected 10 models, which simulate very weak Western North Pacific precipitation anomalies. So like precipitation pattern is like this. Then we will check the teleconnection. So before showing the next slide, what do you expect in next teleconnection difference? So we can expect Croce anticyclone will be strong here and weak here, right? So you are correct. Okay? It's in this case, Croce anticyclone is strong. Okay? But in this case, it's quite very hard to find the Croce anticyclone. That means Western North Pacific precipitation is quite important to explain Croce anticyclone. Okay? Okay, and I may skip this. Okay. Also, we also separate 2 groups, divide into 2 groups. One is weakened Western North Pacific. I mean, from December to January, Western North Pacific is weakened here to here, strengthened here to here. Okay, but because the model is biased, then it's almost, even though I selected a weakened case, but almost same in this case. Okay, this is like a strengthened case. Okay. Then what do you expect in next slide? So weakened a case, maybe Croce anticyclone is considerably disappear in this case. Then in this case, the Croce anticyclone will be strengthened, right? Do you agree? Okay. But unfortunately, you are wrong. partly right. In this case, it's right. It's a Croce anticyclone is like a strengthened because Western North Pacific precipitation is increased, right? But it's a little bit weakened, but not considerable difference because precipitation difference is small. Okay. Anyway, even we are wrong, but it's this result support our argument, right? Okay. So far, I showed some winter case. So during winter case, we found very strong seasonality in terms of El Nino impact or El Nino teleconnection. In December, only December, not January, in December there's a strong crucial anticyclone, which lead to some warm and wet climate condition over East Asia. But in January, this teleconnection is, this crucial anticyclone is abruptly gone, so there's no significant impact. So there's a strong seasonality. There is, due to some forcing, competing tropical forcing. Next, I will show some strong seasonality during summertime, but which is related to some basic state change and the non-linearity of precipitation. Okay, this is a correlation between Inosuke and East Asia precipitation. Like a domain is like it's covered like Korea and Japan, like here. Then we found there's some significant positive correlation, like here, like middle of June to early August, positive correlation. But if you compare this the other summer, like late June or some late August, the correlation is even negative. Okay, so if you check the spiral pattern, so there's strong positive correlation like here, right? But in this period, there's strong negative correlation over the Japan. Then it's also there's strong negative correlation. You see, there's only 5 center difference. The center is about a month difference, but correlation pattern can be quite different. So actually, my colleague is brought this result. Then I thought this is a kind of noise, because during summertime precipitation is quite a big noise. So this is not signal. This is a noise. But I realized this is a signal. I will show that. Okay. So if you look at some large domain, then this is a relation. There are very beautiful teleconnection pattern. Okay. So there is a positive precipitation, and negative precipitation, and positive precipitation. Okay. But in this timing, overall no pattern, just a weak negative, right? But in late August to September, there is a strong negative correlation. So what caused this? Why is this particular season? Okay, that's my question. Then also if you check the teleconnection, so this precipitation make this cyclonic flow here. Okay, this precipitation cyclonic flow. Then this negative precipitation induced some anticyclonic flow here. Then this precipitation is like a precipitation flow. It's kind of some moist loss wave propagation. There's a cyclonic, anticyclonic, cyclonic. Okay, but in September case, there's overall cyclonic flow. I can explain this it's a larger cyclonic flow, but I will skip this part. Anyway, this is like a systematic teleconnection pattern here. But if you compare SSC pattern, almost similar. Okay. So this is a regression. So that teleconnection, this precipitation is important. Okay. This precipitation is quite important. This negative precipitation, because this negative precipitation make this anticyclone here, also cyclone here. Then in this season, there is some southerly wind, which this southerly wind anomaly means some intensified some monsoon flow in low level. Also, this cyclone here is like some front here. This like a gradient can make some more precipitation or heavy rainfall case. So this precipitation is important. So we carried out some LBM experiment. Then we found this precipitation is quite important to introduce this anticyclone. Okay. So far I showed a linear regression that is a mixed up is El Nino and La Nina. If it is due to noise, then some particular event has some strong signal. They make us this kind of some regression or some anomaly. Okay, so I checked separately El Nino case and La Nina case. Then I found it's surprisingly in the case of the El Nino and La Nina, the pattern is quite similar. There are still beautiful teleconnection pattern. Positive, negative, positive. Negative, positive, negative. Okay? That means like a tropical signal. Teleconnection pattern. Okay? This is cyclonic, anticyclonic, cyclonic. It's anticyclonic, cyclonic, anticyclonic. Okay? It's important. So I show some seasonal evolution. So like this longitude, this latitude, and this time evolution. Okay. Then this is El Nino and La Nina. So you see, in the particular timing, always this timing. Okay. In the both case, there's some teleconnection pattern like this. It's meridional propagation signal. Okay. That means some basic state play a role in developing this kind of some teleconnection. So what makes this teleconnection? I found this is a climatological evolution. This is climatological precipitation. So this is time, this is longitude. So in this is like I mentioned the timing. I mean, which has some high correlation of the Korea and Japan. So I found in this season, this is a 20 north, like where that negative precipitation exists. Then I found in the early summer, the precipitation is very low. Also, this is a low level convergence. So there's no convergence. So even there is some external forcing, but if that region is too dry, then external forcing cannot trigger the precipitation anomaly. But in this season, this is already wet, so instability is very strong. So some external forcing can make some precipitation anomaly. So that's why in this season, the meridional teleconnection or meridional propagation take place. So I also checked the variance, a little bit delayed, but in this season, it's like a variance. I mean, interannual variance is very weak because it's too dry, climatologically too dry. But in this season, it's vigorous, it's very active. Interannual variance is very big. That means very easy to make some strong anomalies. Okay. Okay. That's all. So that's my summary. So Western North Pacific and Central Pacific precipitation anomaly has an opposite impact on teleconnection pattern, which make a strong sensitivity of ENSO teleconnection. Also, I want to emphasize this precipitation. Western North precipitation is quite important for East Asian climate or teleconnection. Then this climatic monsoon evolution is quite critical for the summer teleconnection to East Asia. Last will be kind of some take-home message. So ENSO teleconnection is strongly phase locked to annual cycle, even in a sub-seasonal scale. So usually in conventional way, we take some seasonal mean to examine the impact of El Nino. I mean, it's regional impact. But this seasonal mean may not proper to the representing some extratropical ENSO impact. Some small scale analysis will be required.